Thank you for the introduction. Thanks to the organizers for the very kind invitation. This talk is about polynomial maps with biased input distributions. Some joint work with postdoc Davi Castro-Silva, so at CWI. It's about a problem that originated from a question in theoretical computer science concerning error correcting codes. So I'll quickly try and introduce kind of the context of the problem. So for the purpose of this talk, an error correcting code is just a map from n-dimensional vectors to k-dimensional vectors. K is typically smaller than n, but you don't have to remember this for the purpose of this talk. Here, beautiful F will denote a prime field, a field of prime order. And I'm mostly interested in low characteristic regime, so P should be thought of as a fixed prime. Okay. So an error correcting code is a map from n-dimensional vectors to k-dimensional vectors, and it typically has the properties that its code words, points, strings are well separated in Hamming distance. So X and Y are. K is the length of the K is small, N is big. K messages n-dimensional vectors. So for two messages X and Y, the code words EX and EY are usually well separated in Hamming distance. And the purpose of this is that if a code word gets partially corrupted, so some of its coordinates get corrupted, if the number of errors is not too big, then there will be a unique code word at closest distance from the corrupted point, so you can uniquely decode the original message backwards. Very roughly speaking, what error correcting codes are about. So a very basic noise model that models how error correcting codes get corrupted is the binary or the symmetric channel. So the noise model that I'll consider in this talk is given by a random n-dimensional vector, where the coordinates zi are independent, identically distributed, and distribution on them is that coordinate zi is 0 with some probability rho. I'll refer to this as the bias. And with probability 1 minus rho, zi is uniformly distributed over the field. So zi is uniform with probability 1 minus rho. So if rho is 0, then Z is just a uniformly distributed random string. And the goal is in this whole setup is to try and decode the message X. So X lies in F to the K from the corrupted code word E of X plus the noise string Z. So E of X is the code word corresponding to message X, and Z is an error vector that you add to E of X to corrupt it. That's the basic setup here. Good. So the question about error correcting codes that this talk is about has to do with the computational complexity of decoding noisy error correcting codes. And it turns out you can model the particular computational complexity theoretic model by polynomial maps. So a map phi from F to the N to F to the K, so let's descend, say, noisy code words to messages is a polynomial map if it's given by a k-tuple of polynomials. Fi for polynomials, invariant polynomials over the field. And I'll define the degree of this polynomial map as the largest degree among the polynomials that define its coordinates. Okay. And a bit of shorthand, I'll denote the vector space of polynomial maps from f to the n to f to the k by pol f to the. And
Fi is Fi.
What's that?
Fi and Fi.
Sorry, this is Fi, yes, thanks. Okay, and the subscript at most d refers to the set of polynomial maps of degree at most d. Okay. So what do these things have to do with computational complexity? It turns out polynomial maps can be used to represent a very basic family of computational circuits. Very roughly speaking, circuit is something like this. You have some input leaves, which there are n corresponding to the dimension of the vector that goes into our polynomial maps. Some gates that have fan-in at most 2, so they depend on most 2 variables at a time. And then in the end, there are k outputs. Okay. So these gates that I'll consider here, they all have fan-in 2. They depend on at most 2 variables at a time. They take as input an element from FP and spit out another element of FP. And there's one special gate that will allow that doesn't have input or fan-in 2, and that's the parity or the sum gate. So there's one special gate here that's allowed to depend on an arbitrary number of variables, and that's just the sum modulo p. Okay. And this class of circuits is known as NC0 plus. P is 2, characteristic is 2, then plus is the parity.
So it's just one layer and then an output layer, or it can have more?
It can have more layers, yeah, sorry. So in NC0, the depth of the circuit is constant. So there's only a constant number of layers. And each gate, except for the sum or the parity gate, is only allowed to depend on 2 coordinates at a time.
And can compute any function?
You can compute any.
No, the gate can.
The gate can compute any function. Yeah, but it depends on. So there's not too many. It depends on 2 variables. That's right. So it turns out there's a 1-to-1 correspondence between constant degree polynomial maps and these NC0 plus circuits. Okay, you can go back and forth. Any constant degree polynomial map can be computed by such a circuit and vice versa.
So the degree is the depth or something?
The degree is actually extra. So degree is multiplicative under composition. So the degree grows exponentially with the depth, but the depth is supposed to be constant. So in the end, you get constant degrees. Yeah. Good. So my colleague, Harry Buhrman, came to me one day and asked me, given a noisy error corrected code, how well can it be decoded by a linear map? Okay, so I have say phi has degree at most 1, and I feed it a string like this, where z is distributed like that. It's noisy. What's the probability that such a linear map spits out x? Okay, that turns out to be not so difficult. This probably goes down exponentially quickly with k, the message length. So that was not so difficult. Of course, there was more to the question, and then so I gave him the answer, and then he said, well, really the question is what happens with degree D maps, and that was, so he was really interested in what can NC0 with parity circuits do in terms of decoding noisy error correcting codes. Okay, so the problem we considered is what's the probability that a constant degree polynomial map correctly decodes a corrupted error correcting code. And Z is distributed like this, and X is also uniformly distributed. Okay. It turns out Yeah, these circuits or these polynomial maps are incredibly bad at doing this, and that turns out to be a positive thing. And the reason why is that my colleague was interested in this because there's a quantum analog of these types of circuits that can do this type of decoding for a particular code called the Hadamard code. So this, in a sense, shows that quantum NC0 plus circuits are more powerful than the classical analog. That was the gist of the whole project. But the difficult thing turned out to be showing that polynomial maps are bad at this, and that's what this talk is about. So the main theorem I want to discuss says what I just mentioned a couple of times. So the main result shows that there is some constant k0 depending only on d for the degree, some positive parameter epsilon of your choice, and the noise parameter or the bias rho. Such that the following holds. If k, the message length, is sufficiently large, so larger than k0, phi is a polynomial map of degree at most d. And E is an arbitrary map, which you can think of as an error correcting code. The particular properties that are desirable for error correcting codes turn out not to be relevant here. So you can think of E as an arbitrary map from fk to fkn. Then the probability taken over uniformly distributed random message and a noisy z. So I'll denote the distribution I defined up there by beautiful n sub rho. The probability that this map phi correctly decodes the corrupted code word e of x plus z to x is at most epsilon. So this is for any epsilon of your choice. And then this holds if the message length is sufficiently large.
Is E a linear code?
No, it's an arbitrary map. So
Is there the proof for linear? Or it doesn't?
I don't know how to use that information. Yeah, so the original question concerned the Hadamard code, which is linear, but even there I couldn't see a natural way to incorporate that information. Yeah, maybe there is. Okay, so my initial hope was that there was some off-the-shelf results from higher order Fourier analysis that would shed light on this problem. So in particular, if z is unbiased, so rho is 0, then here you're looking at a uniformly distributed z and something like equidistribution for a polynomial map. And there's beautiful results about this, but I'll try and mention quickly. So in the unbiased setting, so that, yeah, it doesn't pop up here. This holds for arbitrary n. If n is much, much smaller than k, then this is in a sense trivial because you're compressing messages, right? In the typical applications, n will be larger than k, but k will not be constant. That'll be relevant in what I'm about to talk about. So in the unbiased setting, there's this definition of rank for polynomials, which you can use to further define the notion of rank for polynomial maps. Given a function f to the n to f, Green and Tau defined the d rank of this function as the smallest integer r, so that you can write this function, some other function of r polynomials as degree is at most d. Okay. So, yeah, rank d of a function. So based on this, you can define a notion of something called regularity, which is supposed to capture a notion of randomness of a polynomial map. So a polynomial map, degree d, is R regular. If for every non-zero vector v in, to the k, the rank d minus 1 polynomial you get by adding up the polynomials to give you the coefficients of phi with the these coefficients of v has rank at least r. Okay, sorry, this is for non-zero v. So we're considering here linear combinations of the polynomials that define the polynomial map phi. Sum in one map, and we want all of these linear, non-zero linear combinations to have high rank. In this case, we say that phi is R regular. There's a theorem of Green and Tau that says that if a polynomial map implies that if a polynomial map is regular, then you have an equidistribution phenomenon that gives you an upper bound like this. So Tau proved that phi is regular in the sense phi is regular, then I'll paraphrase the result slightly to make it look like the thing I'm after. For every vectors y and v, the probability over the uniform noise vector now, phi of z plus y, so maybe think of y as a code word, is equal to v. You can think of v as a message you're trying to decode, bounded from above by some epsilon, parameter epsilon, depending only on the degree. I think it's field dependent and on the measure of regularity. So it's R regular.
This is for characteristic greater than d.
This is for characteristic greater than d. Okay. Okay, so this looks very nice, but there's a number of reasons why it's not so clear how to use this to prove the result I'm after. So first of all, the map phi that I'm presented with doesn't have to be regular. Okay. Now this in the paper where they prove this, they have this really nice procedure whereby they can in a sense force phi to be regular. You can regularize phi, which roughly speaking means that phi behaves regularly on a partition of f to the n given by algebraic sets. Okay. Okay. But there's further issues, which is that, so one is that in our case, Z is not uniform, but it's biased. And I don't know what a biased Z looks like when you restrict it to an algebraic set. And another thing is that this regularization works well if K is very, very small in terms of n, just constant. But in our application concerning error correcting codes, K typically grows with n. The Hadamard code, for example, K is log n, and this regularization doesn't buy you anything anymore. So unfortunately, this really nice result doesn't seem immediately applicable to this setting.
In your case, the characteristic is also bigger than D, or
no, it's not. No. So I'm interested. Like I said, I'm interested in.
So this is true also for small characteristics, but it's not a theorem of Green and Tau. It's the theorem of Tau and me. But there are quantitative results of this form by Luca.
Good. Yeah. So I'll mention. Yeah. So in the end, we did end up using a result like this. I'll mention that. In a bit. Yeah. So I'm aware of some, but possibly not all of the results of this shape, but I'm aware that it's been refined a bunch of times. And there's one particular refinement that turned out to be useful, but for a slightly different reason. All right, so I mentioned that phi doesn't have to be regular, and there's no way that we can force phi to be regular. And then the next option that's typically explored in additive combinatorics is a structure versus randomness paradigm. So somehow you consider case analysis, either phi is regular, and then hopefully it behaves randomly, and a green tau-like equidistribution theorem applies, or phi is not regular, and then phi should have some structure you can exploit. And that turns out to be a strategy that was useful in this setting. And to see that's useful, it's already quite nice just to consider the linear case where you see this happen. So if phi is a linear map, given by some k by n matrix U, so maybe think of it as a short fat matrix U, you can consider two cases. In the first case, the rank of U is small. The rank of U is at most k over 2. Well, then the probability over a uniformly chosen random message, x and f to the k, that phi of b of x plus, say now, some fixed noise vector v, we can incorporate it later, is equal to x. This event happens only if this x lies in the image of a coset of the image of u. Most of the probability that this x lies in the image of u plus this vector v. But since the rank of u is at most k over 2, this happens with exponentially small probability. So in the low rank case, structured case, yeah, you get exponentially fast decay of the success probability for decoding by linear maps. So somehow the structured case. The quasi-random case, where the rank of u is large, say at least k over 2, instead of considering the vector x, we'll consider the randomness in the noisy vector z. So in this case, probability over z distributed according to n rho, that phi of say z plus e of x to whatever x. You can write this kind of nicely by looking at the distribution of z. So z is a random vector where the coordinates are independent from each other, and each coordinate is either 0 with probability rho or uniformly distributed with probability 1 minus rho. If I want to split the distribution of z up in two parts, first I'll select the coordinates of z that are 0. Okay. So this is a random subset. And then I take a uniform distribution on the remaining coordinates. So I can write this random vector z as a distribution over random subsets, Bernoulli random subsets, that include each element with probability rho. And then a random vector, uniformly distributed random vector y, whose coordinates just belong to this subset. Okay. So the z will look like y on the coordinates in I, and it's 0 elsewhere. It's an equivalent way to write this noise. So once you've done this, you can write this event simply as the event that the restriction of u to the columns indexed by I y is equal to some fixed vector w. Okay. Good. So what can we say about this this restricted vector or restricted matrix U? So here we have U, say. So U has large rank at least k over 2. So there are at least k over 2 columns that are linearly independent. This Bernoulli random set selects each of these columns with probability 1 over rho. So with very high probability, this random set I will contain a significant fraction of these linearly independent columns. That means that with very high probability, this random matrix U sub I will have high rank. And if it has high rank, a random vector Y will satisfy this linear equation with very low probability. Okay, so if you work this out, you again get exponential decay. Rho times K. Okay, so here you see the structure versus randomness in action in the linear case, where you use matrix rank to separate the structure case from the quasi-random case. And it turns out the same thing works to prove this result for higher degrees. But now we use a different rank function than matrix rank. So we introduce a new rank function for polynomial maps that we call the analytic rank. So for a polynomial map, phi of degree at most d, we define the analytic rank, a rank sub d of phi, that's minus the logarithm base lowercase p. So p is a characteristic of the field I'm working over. I'm just suppressing it to lighten the notation of the maximum taken over polynomial maps whose degree is strictly smaller than d. Probability over a uniform vector y that phi of y is equal to y. Okay. Give you a moment to parse this. I'm assuming that phi has degree at most d. We're taking a maximum over polynomial maps psi of degree strictly less than d, and I'm looking at the proportion of points on which phi and psi agree. Small example of the matrix case, and there we'll see that the matrix rank pop up again. Phi is again the linear map I considered before. And to see that this gives you the rank of U, it suffices to compute the probability over uniform y. That phi of y is equal to some fixed vector w. That probability is exactly p to the minus the rank of U. If the difference of W and V lies in the image, and it's 0 otherwise. Okay. So to maximize this probability, we should choose W so that this difference lies in its image. Okay. So this motivates considering possible other polynomials than 0 here. Okay. If you do that, you get the matrix rank back in the linear case. So why did we call this analytic rank? Currently, it's mostly for aesthetic reasons. It bears similarity to something called analytic rank that was defined for tensors by Gowers and Wolf. Tensor can also be considered as a multilinear map. So say a D tensor, that's multilinearly on the Cartesian product of D copies of f to the n. And the analytic rank of tensors, as it was defined previously, is based on a notion of bias. So the bias of this tensor is simply the expectation over independent, uniformly distributed random vectors, y1 up to yd. So omega here is a pth root of unity raised to t evaluated with this d2. Omega is e to the 2 pi for p, and p is the characteristic of it. So this is the bias of the tensor. And you can relate this to the kind of expression I've written down for a definition of the analytic rank. This is equal to the probability taken over independent, uniformly distributed random vectors y1 up to yd. That the polynomial map defined by t, you get by feeding it only d minus 1 vectors and leaving the last coordinate untouched. So it spits out another vector, in this case n-dimensional, is equal to 0. Okay. So you should compare that with the expression here where psi is equal to 0 and phi is a multilinear map now of degree d minus 1.
Correlation with a smaller degree polynomial.
Yeah.
Yes.
Yeah.
It's like whatever comes from the inverse theorem when applied to lower degree polynomials.
Right. Yeah.
Yeah.
Okay, sounds like you have some interesting
No, I think.
information. Okay, perhaps we can talk about it later. Okay, so then the analytic rank of the tensor was defined by Gowers and Wolf as the minus logarithm base p of the bias of t. Okay. Now the question, okay, so for this reason, for this aesthetic reason, we call this thing the analytic rank of polynomial maps. And now the question is if these two things are equal for these multilinear maps. So is the analytic rank of this tensor equal to the analytic rank? I should give it a subscript d here because it's defined only for polynomial maps of degree. Most d is the way I've written it there, of the polynomial map naturally associated with t. So t here is a d-linear form, and the polynomial map that defines is a degree d minus 1 polynomial map that you get by only considering inputs the first d minus 1 coordinates of t. So I don't know the answer to this. So it would follow if indeed for multilinear maps, this is maximized when psi is equal to 0. I don't know if that's the case.
Give an example of mapping with high rank.
An example of a mapping for which this is large? Yeah, random mapping. So a random mapping.
Yeah, but like an explicit.
C.
Well,
I mean the matrix. So d is equal to 1
Yeah, for higher.
for higher degrees.
kind of high rank, like high regular, like some xi cubed or something.
Okay, there's some sums of powers.
Yeah.
Yeah, that should work. Oh wow, I still have a board left. Okay, so to prove this this result, we ended up using a structure versus randomness strategy, where we use the analytic rank of the polynomial map kind of as a threshold to determine if the polynomial map is quasi-random or regular.
So your result is in high characteristic or in every characteristic?
Every characteristic. And we're particularly interested in the low characteristic, because in the low characteristic regime, you have this perfect translation between these NC0 circuits and polynomial maps. High characteristic regime, that breaks down. So it's for the application, low characteristic was relevant. Yeah. In the high characteristic regime, this proof can be simplified somewhat. You can reduce everything to the tensor case. Characteristic is high enough, you can divide by something factorial.
So by high or low, you mean relative to n or relative to the degree of the polynomial?
Relative to the degree. So still constant. Okay, so based on this notion of analytic rank, you can now mimic the proof that worked in the matrix case. So in the structure, in the first case, you consider what happens if the polynomial map has low analytic rank. Case. which means that you're going to assume that the analytic D rank of your map is at most some threshold R that you have to choose judiciously later. Okay, so some parameter R that you need to choose later to make things work. Good. So now, based on this assumption, we want to prove that this probability up here is going to be small in terms of K. And here, it turns out there's a very nice theorem that's very much related to the discrete tau theorem that was proved by Kaufman and Lovett. So what they showed is that there is some positive integer S, depending on the degree D, and a parameter epsilon of your choice. Such that if a polynomial is biased, so if a polynomial P has degree at most D, and bias at least epsilon. So here bias is defined analogously and as the way I've defined it for tensors. You just average the pth root raised to the power p over uniformly random input. So if the polynomial p is biased, then it turns out to be structured in very much the way that Green and Tau defined the low rank, but with a little bit more information. It turns out you can write p as some function of the multiplicative derivatives of p in some directions h1 to hs, some directions h1 to hs to the end. Here are these multiplicative derivatives. P are defined as p of x plus h minus e of x. In particular, these multiplicative derivatives have degree strictly less than the degree of p. Okay. So this shows that large bias implies low rank in the sense of Green and Tau, but the polynomials you need are also somewhat explicitly given in terms of p. Okay. And this turns out to be quite useful in the structured case here. So what does the structured case mean? So if we assume that our polynomial map phi has a low analytic rank, and that means that there is some polynomial map psi whose degree is strictly less than, or is at most p minus 1. So if you define the polynomial on n plus k variables, p, y of v is the inner product between v, the difference between psi of y, phi of y, and psi of y, then this p is biased. Okay? So the assumption that the analytic rank of phi is small implies that there is some psi of lower degree, so that this polynomial is biased. Okay. So polynomial has the property that it's biased is at least e to the minus r. Now we can apply the Kaufman-Lovett theorem to this polynomial to get kind of a reduction of the statement I have up here, but for lower degree polynomials. There's a small calculation you can do now by expressing the indicator function for the event that phi of e of x plus z is equal to x in terms of the pth root of unity raised to this polynomial p, that's possible. Then doing some Fourier analysis on this function gamma, some basic Fourier analytic arguments, Holder, Parsifal, Cauchy-Schwarz, to conclude that the probability over a uniform X and a noisy Z, phi V of X, Z is equal to X. This is bounded from above by P to the S over 2. So S here is some constant, depends only on the degree of this epsilon of our choice, times the probability of a similar expression, gamma X, Z is equal to X, for some gamma whose degree is strictly smaller than that of psi. Some polynomial map gamma, so gamma in all of degree at most d minus 1 up to the n up to the k. Okay. So to go from here to here is a bit of calculation, and it uses this theorem. The point of this is that we now reduce the problem of bounding this by the similar problem, but for one lower degree. And this suggests that an inductive argument might work, provided you understand the quasi-random case. This is the low rank setting. Yeah.
So you're adding more variables and then you get rid of them somehow?
You're adding more variables and not.
You said you have a polynomial and more variables that's biased.
Yeah, right. But this polynomial is just kind of an auxiliary thing. So this polynomial allows you to express that probability. So the indicator function for the event that that happens as an average over V of this polynomial when Y is substituted with an expression like E of X plus. Okay. So the number of variables is just another way to rewrite this indicator function. Yeah. Okay, so in the end, yeah, the structured case suggests an inductive proof, provided you know what to say in the regular case or the quasi-random case. So that's the next thing I want to discuss.
I'm still learning about this bias business. Here, there's no condition on the characters.
It holds for all fields. If I recall correctly, S doesn't depend on the field.
Well,
The point is that it does work over low characteristic.
High characteristic, it's uniform, and for low characteristic, you can uniformize by that. Yeah, this holds for all characters.
So what was important for us is that it in particular holds for low characters.
Non-quantitative.
I see. Yeah, so the S is terrible. So in the end, we get terrible bounds on the K0 in part because of
But in
this
the
result.
characteristic case, the S is very good.
Yes, that's right. Okay, so complement of the structured case is the quasi-random case, where you assume that the analytic D rank of psi is large. Strictly larger than R. Okay, so I did the matrix case. In the high rank setting for the matrix case, what turned out to be useful is to study the rank of random restrictions of the linear map, the linear component of the map phi. Okay, so what we needed in the linear case was the fact that random restrictions of our map to relatively dense subsets still have large rank. That's what's happening in this step here, and that turns out to be what you can use in this case as well. So there's a random restriction lemma. Which says that there is a positive integer R, depending only on D, some parameter sigma, and an epsilon of your choice, kappa, depending only on the degree and epsilon of your choice. Such that if a polynomial map phi of degree at most D has analytic D rank, at least this parameter R, then its random restrictions to a Bernoulli random sigma set will have a large rank with high probability. So probability over a Bernoulli random set that includes each element, so each coordinate with probability sigma, that the analytic D rank of the restriction of phi to this subset is at least kappa times the analytic D rank of phi itself is at least 1 minus epsilon. So this restriction here is what you get by restricting phi only to those vectors that are non-zero or that are zero outside of the set I. Okay. That's the random restriction lemma. And using the random restriction lemma, you can get that's what you can call an equidistribution or a biased equidistribution theorem that implies the quasi-random setting of Riemann theorem. So as a corollary, equidistribution it says that there is some positive integer r, depending only on d, rho, and epsilon. Such that if, say, phi is a polynomial map of a degree at most d, and analytic D rank at least R, then for any vectors y and v, it holds that the probability over a noisy z, so z distributed according to n sub rho, that phi of z plus y is equal to v is at most epsilon. Okay, so this is like an equidistribution, but for biased inputs for regular phi, if you will. Okay. So the core of the quasi-random setting is this random restriction lemma. And there's a way you would like to prove this, which you get inspired by if you consider the matrix case. So suppose that you have a matrix, and you know that its rank is at least R. You know that there are linearly independent rows. So now suppose that you sample these rows according to a Bernoulli distribution. Then with high probability, you're going to sample a significant fraction of them. So with high probability, say a random set I is going to contain a significant fraction of the linearly independent rows. Now, if you independently sample from this subset, if you now independently sample columns with high probability, you're going to sample also a good fraction of the linearly dependent columns from this subset I. And so with high probability, the random restriction of a matrix will have high rank because it contains a high rank core in a sense. Okay. And this uses the fact that an n by n matrix of rank R contains an R by R submatrix of rank R. Okay. And that's the kind of thing you would hope to use to prove a random restriction lemma like this, but nothing like that is known for the analytic rank that we defined, nor is it known for any of the other rank functions defined on polynomials, polynomial maps, or tensors like slice rank, partition rank, analytic rank, geometric rank, you name it. I'm not aware, I don't think it's known whether they contain high ranks restrictions.
For large rank, or large fields, large characteristic, you have the algebraic independence, almost like the rank. It will be R algebraic independent subset.
This is relevant for which notion of rank?
Just algebraic independence for large characteristics.
Not sure how to.
Dimension. Algebraic rank, just like the Jacobian matrix would be the rank of the Jacobian matrix.
Right. But that, okay, so what's relevant here is high rank under coordinate restrictions, and that seems to be a complicating issue for all of the existing notions of rank. Perhaps we can.
That's for large fields.
Okay, yeah, this is okay. So this is also important for small fields. That's the way we use it. Okay, so I'm running out of time. I'm trying to make some decisions on what to skip. Right. So the gist of this is that we don't prove the random restriction lemma using any kind of assumption that there is a restriction whose size is, say, linear in the rank that has rank at least linear in this rank. Okay, we don't exploit something like that. Instead, we use some techniques from analysis of Boolean functions. Seems to me like a property like the thing that holds for matrices would be the nice thing to do. So such a property is conjectured by Karam. I just want to mention the conjecture and then ask the natural question for the analytic rank and conclude. So just over summer, a paper came out by Thomas Karam, in which there's a number of very interesting things. One thing is to pose a conjecture that says the kind of thing that I mentioned for matrices. So he conjectures that there are constants, C and C prime, such that if a 3 tensor, so the C and C prime here, they should probably depend on the order of the tensor, but let me restrict to 3 tensors for simplicity. If a 3 tensor T has slice rank at least R, then there's a subset I whose size is at most C times R, such that principal subtensor of T defined by I has a rank at least C prime times R. Slice rank C restricted to I by I is at least C prime times R. So this is not known to be true. If this were true, then you could prove the random restriction lemma for tensors in slice rank. And this linear dependence, I don't know how to prove it if this dependence is not linear. It's even polynomial, then proving that, I'm not sure how to do.
Is this a symmetric tensor?
No, it doesn't have to be.
But you still want all the i's to be the same?
Yeah, it doesn't make a huge difference. Because if you have 3 of them, then you can just take the unions. Yeah. So for the same reason here I chose I and J independently, but you could choose afterwards, you could just choose the union and it's still Bernoulli distributed. So it doesn't make a huge difference for tensors. So Karam did prove a theorem along the lines of his conjecture, but not with linear dependence. Okay, so instead, I think the size I is maybe exponential in R, and the lower bound on the restricted rank is maybe polynomial in R. It's already very good. You don't have Ackermann type functions, but it's not good enough to prove the random restriction lemma. So let me finish by posing the natural question, which is if this conjecture is true in the case of polynomial maps and analytic rank. So is it true that if phi is a polynomial map of degree equals to d, then there is some subset of the coordinates of size, say at most some constant, depending on the degree times well, summations. Yeah, the analytic D rank phi, such that the restriction of phi to this set as analytic D rank at least omega of that. So such that the analytic D rank of phi restricted to I is at least omega of D times. So if this were the case, then it would be relatively straightforward to prove the random restriction lemma. Now it's somewhat less straightforward, although maybe proving this is very difficult. The combined proof could then be more difficult than it is currently for the random restriction lemma. But this seems like a very natural property for rank functions to obey. So that's the main question I want to leave you with, and I'll leave it here. Thanks.
Thanks very much for the talk. Are there more questions?
So you care. So you didn't say anything about how you prove this. So you said you care about K growing with N, or
Yeah.
So how and where and what didn't appear.
No, so in the result, the dependence of K on N or vice versa makes no appearance. The only thing that's relevant is K here.
Where
So
does
you can
it
choose R.
Where? But you said you do care about this. So where does it make an appearance? So where is it?
So
I thought you said something when you mentioned at the beginning that.
yeah, so
Care
at first I wanted to see if the result of regularization might work, right? But there that works only if K is constant. And in the applications where you have some aircraft code, K is not constant. So regularization doesn't really.
So how does K? I understand, but you didn't say. So how non-constant do you need K to be, or what do you need from K?
Okay, so the particular aircraft code that was relevant in this setting has K equal to log N.
Okay. And what's blocking you from making this quantitative, except for only the results, only the Kaufman-Lovett?
No, so in the end, the random restriction lemma is proved by induction on D, and that also seems to incur some bad bounds on this R. But I think that the worst culprit is probably Kaufman-Lovett parameter. In the high characteristic regime, this gets much better. So you could replace Kaufman-Lovett by, I guess, the polynomial relation between analytic rank and partition rank by Janser and Ilichevich. And then you get much friendlier bounds.
Then, okay, then what do you get? What do you lose from your restriction?
So
What bound would you get?
in the restriction, let's see, so also in the high characteristic regime, in the restriction, you can reduce to the tensor case. Let's see, so right, so in the high characteristic regime, it suffices to prove the random restriction lemma for the multilinear form that's defined by the highest degree component of this phi. And in that case, this random restriction lemma, it's much better. It holds that, right, actually K is an absolute, you can choose K to be an absolute constant, and you don't need an assumption on R for tensors in the high characteristic regime.
What would you get?
What do you mean? What
bound would you get?
Where? Here?
Yeah.
Yeah, so here you get that, in that case, you get exponential decay with K in the high characteristic regime. In the low characteristic regime, you get something awful.
Okay.
But so I conjecture that even in the low characteristic regime, this would drop off exponentially fast with K.
The analytic rank for tensors only can go down when you apply a linear map on one of the slides, one of the directions. Is that also true for your analytic rank? Polynomial maps?
So you want to compose it with a linear map?
Yeah.
Yeah, I suppose it can only go down. That's right. Yeah. Yeah. So this thing has a number of nice properties. It's non-negative, monotone under restrictions, it's sub-additive, and it has a Lipschitz condition. So that's kind of a general set of properties we use to prove this. And that's also why you can prove this for tensors and any of the other rank functions that are out there for polynomials, polynomial maps.
It's sub-additive.
Sorry?
It's sub-additive.
Yes.
Yeah.
Are there other noise models that are you can do this with, or they're interesting to us?
I don't know. So, I mean, all this very heavily uses the fact that coordinates are independently corrupted. So yeah, you either corrupt it with some probability or you do something else with the opposite probability. So coordinate restrictions kind of naturally make an appearance with this noise model. What you do if there is corruption, so here we take a uniform distribution. I suppose you could take a different distribution. And I think that was studied very recently by Karam and Gowers. See this, biases of polynomials under biased distributions. So if you consider a polynomial, normally to compute the bias, you take a uniform average. So they have some results that pertain to a situation where instead you take a coordinate-wise uniform distribution over a subset of your field, say. But I don't know if that's a natural thing to assume in noise models. This is a very basic and natural noise model.
Right. Any more questions? All right, so if not, let's thank you up again.